turn to the question of electrochemistry now. And electrochemistry has always been a very important part of chemistry. That is, the idea of using a chemical reaction to generate a flow of electrons through an external circuit has been always an important subject. But today, as we move into the future, electrochemistry has leapt into the future of not only intense chemical research, but also the development of technology for generating energy, for storing energy, and so it plays a crucial part in the intersection of global energy production and climate. And you can see from the title of Chapter 7 that electrochemistry represents the union of Gibbs free energy, delta G, and electron flow, and unites that to chemical transformation. And we'll see that the engagement of electrochemistry ties the change in Gibbs free energy to the voltage of a cell, and that connection turns out to be extremely important across broad landscapes of chemistry. So let's look at the goals. Our first part of this study of electrochemistry has this remarkable capability for linking all of the chapters that we've studied prior to this. It also allows us to revisit the energy flow in economic structures, and we pick the United States as an example to show how important electrochemistry is to our future. The next thing we look at is that we're going to link the chemical potential, delta G, to the electrical potential, which is the voltage produced by our electrochemical cell, and we want to relate that back to gravitational potential, mass times acceleration of gravity times the height through which a mass falls within that gravitational field. And when you look at these three aspects, they appear to be very, very different. But through the genius of electrochemistry, it turns out we can unite all three of these. Then we want to examine oxidation-reduction reactions, particularly with respect to metals in solution, because that's how we're going to divide oxidation from reduction that will allow us to create an electron flow through an external circuit that can do work, heating, bringing light, driving automobiles, all sorts of different aspects. And then finally we want to develop the ideas of anodes and cathodes and link that back to Gibbs free energy. Before we dive into the details of how electrochemistry works, it's interesting to step back for a moment and recognize how important electrochemistry has become to the global endeavor. And we can start by looking at high-speed rail. These new trains move at 350 kilometers per hour, and they represent a massive change in both the way many countries do transport people and the efficiency by which that transportation is executed. The next thing we look at are electric automobiles, and we'll see when we do the calculation of how efficient an electric automobile is that it represents a major breakthrough in carrying not just people but freight, because it turns out the larger the vehicle, the easier it is to convert it to electric power. And it's also true that when you look at the performance of electric automobiles, they vastly exceed the performance capabilities of gasoline-powered or diesel-powered cars. Then we turn to the question of scientific research related to electrochemistry, and this is a lithium-ion battery, and this is a remarkable battery because electrons flow through the external circuit while lithium cations flow through the internal circuit. And the energy that's driving this combination results from the combination of those electrons with the lithium cations. And there's a huge amount of research internationally going into the capability and improvement in these battery systems. Then we have a new battery technology based on the flow of materials into and out of the anode and cathode. And these flow batteries can contain a massive amount of energy, and they become very important for bridging the renewable energies of wind and solar during periods of either low sunshine or low wind velocity, and these flow batteries are becoming extremely important to emerging research. But electrochemistry plays additional roles. One of the most important aspects being developed is the capability to draw carbon dioxide out of the atmosphere by passing it through a fan system that can extract that carbon dioxide and then sequester that carbon dioxide under the earth. And as we'll see when we continue to develop the ideas surrounding the irreversible changes in the climate structure, that we have to bring CO2 concentrations down below 300 parts per million to reestablish a stable climate. And of course, working against that is the release of CO2 from fossil fuel combustion. And we will see that some 10 gigatons of carbon is released per year by the release of carbon dioxide and methane from extraction, distribution, and combustion of these molecules. And we are also becoming acquainted with the fact that as we put more and more carbon dioxide into the atmosphere, we're driving up surface temperatures that increase the water vapor concentration in the atmosphere, and that manifests itself in more intense storms that lead to flooding. It also creates a very rapid breakup of glacial systems, for example, in Greenland, which increases sea level. So it's a combination of intensive storms dropping water, intensive storms providing wave heights that can swamp cities along the coast, and then finally the permanent and irreversible rise of sea level. Electrochemistry plays other important roles. For example, modern developments in photovoltaics sit at the cusp of revolutionizing climate research globally, provide the capability for solar-powered stratospheric aircraft that can fly for months non-stop. The observations that can be provided by the 12 months of continuous flight with these systems provides insight into the climate structure that can only be obtained by this technique. And then finally, all living organisms are sustained by electrochemistry through the conversion of ATP to ADP in the cell structure. So as you can see, electrochemistry plays a fundamental role all the way from sustaining life through to developing new techniques for sustaining humans at the global scale.